Okay, here we are, crew. These are our 8.3 notes. We're going to look at graphs of exponential functions, and we're going to use them as we have before, both to evaluate and to solve exponential equations in order to answer questions. But we're going to add a focus, and that focus is on horizontal asymptotes. So let's start here with this idea. A function will have a horizontal asymptote, and we know that a horizontal asymptote is a horizontal line, which will always have the equation y equals a constant. If that function will take on values, right? So the function values are the y coordinates of points. So if the y's get closer and closer to some number, that's our constant, as x's get very large in either the positive or the negative direction. Okay, we say that mathematically in this way, right? And that is that the limit of f of x, right? F of x is the y coordinate of a point, will equal c as x goes to positive or negative infinity. Let's look at a graphical example of that idea. So here I have the graph of a function. So this is my function, f of x. And my job is to find the limit of that function 2 times. Once as x goes to positive infinity, and the other as x goes to negative infinity, and then write equations of any horizontal asymptotes. So the idea here is this. If I'm going to find the limit as x goes to, this says negative infinity, then I'm going to start at any point on my graph. It really doesn't matter where. And I'm going to follow that graph in the direction that x's go to approach negative infinity. Well, that means I'm going to go to the left on this graph. And as I go to the left on this graph and follow it, I want to think about what is happening to the y coordinates of my points. So here I have a y coordinate, right? Here I have a y coordinate that looks like it's a little less than 1. Here my y coordinate is about 0. Here my y coordinate is about negative 1. And as I follow along this graph, as it travels to the left, my y coordinates are getting smaller and smaller and smaller. But as we move along this graph, the graph of my function is leveling out, and it's leveling out closer and closer to negative 2. So my limit is negative 2, and I have a horizontal asymptote at y equals negative 2. Let's look at it the other direction. So this time we're going to look at the limit as x approaches positive infinity. So I'm going to jump on my graph, and I want to follow this graph in the direction where x's get closer to positive infinity. Well, that means I want to follow this graph to the right. And as I follow this graph to the right, we can see that it is leveling out on the right end. And those y coordinates of my points, right here it's a little more than 1. Here my y coordinate looks like it's about 2, and here my y coordinate might be 2.5. So my y coordinates are getting bigger and bigger and bigger, but as I follow along this graph, they're never getting any larger than 3. 3 is my upper limit. So my limit is 3, and I have a horizontal asymptote at y equals 3. Here's another example. Right? So here, right, I have another graph, and if I want to find the limit as x goes to negative infinity, I'm going to jump on my graph and I'm going to follow it to the left. Well, as I follow it to the left, I am also going down, and I am going down without leveling off, without limit, right? And the y coordinates along this graph get smaller and smaller and smaller, right? That limit is not a number, but we can say it's negative infinity. And what that means, right, this is not a constant, so there is no horizontal asymptote on the left end. Right? If in contrast I want to find the limit as x goes to positive infinity, then I'm going to jump on my graph, and x's go towards positive infinity as they move to the right. So I'm going to move to the right. And as I go to the right, my y coordinates go from here about 1/2 to here my y coordinate maybe a little more than 2 to here my y coordinate maybe 1 1/3 or so, and my y's get smaller and smaller and smaller, but never any smaller than 1. Right? Y equals 1 is a horizontal asymptote, and the limit of my function as x approaches infinity will be 1. So when the limit's a constant, y equals that constant is the equation of my horizontal asymptote. Okay. All right, kind of getting that idea. Let's look at this from another example. Okay, my job here is to graph a function, so I'm supposed to sketch the graph of a function where this says f of x goes to 3. That means gets closer and closer or approaches 3 as x goes towards infinity. This is just another way of saying the limit of f of x is 3 as x approaches infinity. Right? And if my limit is 3, which is a constant, then that means that I have a horizontal asymptote, right, of y equals 3 on the right side. So you can see that at 3, right, I have drawn in a horizontal asymptote to the right. This statement here says that my limit of f of x as x approaches negative infinity, so off to the left, equals -4. -4 is a constant. So you can see that I have drawn a horizontal asymptote at y equals -4 to the left, right? Because x's go to negative infinity as they go left. So here's my horizontal asymptote, and it approaches -4. So my job is to graph a function, right, that would behave that way. So if I have my function, let's say that it contains this point, maybe that's 0, 1, I guess, right, that my function is going to increase and then level out to the right end at y equals 3. To have a horizontal asymptote of y equals -4, it's got to go down and level out, right? So leveling out that way. So that might be a graph. Now there are lots of them. I could even do a graph that looks something like this. Let's say I start at this point, right? And this point actually goes up and down and up and then levels out here. Let's say here it comes in and it crosses over and then comes in and levels here, right? So that also has a horizontal asymptote to the left of y equals -4 and then to the right of y equals 3. So that defies the understanding that a horizontal asymptote is a line that a function never crosses. This red function crosses, right, horizontal asymptotes several times. So it's not about whether it crosses or not, it's about how it behaves at the ends that determines that there's a horizontal asymptote. All right, so with that understanding and our knowledge of exponential functions, we're going to pair what we know about graphs of exponential functions with finding limits as x approaches positive or negative infinity. Right? So let's start with this one. Okay, so I'm going to start here with A. I want to find the limit of the function defined by 4.2 times 0.7 to the x as x goes to infinity. Right? This is the general form of an exponential function. From that equation, I know from 4.2 that my function is going to have a y-intercept there, 4.2. My b value is less than 1, so I know my function is going to be an exponential decay function, and exponential functions, right, have horizontal asymptotes at y equals 0. So as x approaches positive infinity, goes off to the right, the limit will equal the location of that horizontal asymptote, which is 0. Let's look at another example. So look at B. Here I'm finding again the limit of an exponential function in general form. I know from 120 that the y-intercept will be 120, And I know because my growth factor is greater than 1 that it will be an exponential growth function. I am trying to find the limit as x approaches negative infinity. So I'm going to follow this graph off to the left, right? And that function is approaching its horizontal asymptote, which again is at y equals 0. So I know that this limit is 0. Okay, let's take another more complicated example. Okay, so here we're going to look at C. Here I want to find the limit of this function that's defined as 2.5 times 4 minus 0.5 to the x. Right? That is an exponential function because I have x in an exponent, but it is not in general form. So we're going to work with that. And the first thing we're going to do is we're going to distribute this 2.5. So 2.5 times 4 gives me 10. Right? So I have the limit of 10, right, minus distributing this 2.5. I have 2.5 times 0.5 to the x. And we're going to learn a lot more about limits in the 4th quarter this year as we kind of get closer to calculus. But one of the property of limits is that if we're finding the limit of a function that is the sum or difference of two separate terms, then we can find the limit of each individually. So this one limit of all of this is the same thing as the limit of the first term. So the limit of 10, right? Then because this is minus, the limit of the rest, which is the limit of this 2.5 times 5 to the x. Right? So for me to find the limit of 10, I'm going to draw the graph of y equals 10. And to find its limit as x goes to infinity, I'm going to follow it to the right. And as it goes to the right, all of its y coordinates stay 10. So its limit is 10. Now I'm going to look at the limit of 2.5 times 0.5 to the x. This is an exponential function in general form. The 2.5 is my y coordinate. And this 0.5 is my b value, which is less than 1. So I know that my function is decaying. If I want to find the limit as x goes to infinity, I'm going to follow it to the right. I have a horizontal asymptote at y equals 0, so that limit is 0. A little bit of math to do, and my final limit is 10 minus 0, which is 10. Right? So limit's a relatively new concept to us, but not hard to find from the horizontal asymptote of exponential functions. All right, let's talk a little bit more about graphs of exponential functions. So, it's kind of summary. We know that a graph of an exponential function, which is in general form a times b to the x, will be a growth function if the growth factor is bigger than 1. It'll be a decay function if the growth factor is positive but less than 1. In both functions, they extend forever left and right, so their domains are negative infinity to infinity. Both functions lie above the x-axis, so they have a range of 0 to infinity. Right? In a growth function where b is greater than 0, its tone, how it behaves, is increasing, whereas the decay function is decreasing. Right? Both are curves that would be part of a bowl. Right? They're curving upwards, so we say that their concavity is concave up in both cases. Both have a y-intercept of a, which is the coefficient of the power in the equation, right, the initial value of the function. Both have horizontal asymptotes at y equals 0. Because the growth function approaches that horizontal asymptote to the left, its limit as x approaches negative infinity is 0. Right? But to find the limit as x goes to positive infinity, we would follow that graph to the right. It continues going up, so its limit is infinity. Right? For our decay function, it approaches its horizontal asymptote to the right, so its limit as x goes to positive infinity will be 0. right? But if we follow it to the left, that function keeps going up, the y's get bigger and bigger, so the limit as x approaches negative infinity will equal infinity. So most of that review. So now let's look at the effects of parameters a and b, right? And again, this should not be terribly new, but we know that the a and b, right, are a, the coefficient of our power, and then b, the base of our power. So since a, right, since a gives us our y-intercept, as a gets bigger, the y-intercept gets bigger. So you'll notice in these equations, right, they all have a 1.2 as a base, but our our a values, our initial values are different, and the function with the lowest a value has the lowest y-intercept, the function with the largest a value has the largest y-intercept. On the other side here, what we have are functions that have the same a, but they have different b values. When b is positive, the graph is going to curve up because we have growth. So when b is not less than 0, but less than 1, still bigger than 0, it's going to curve. Oh, I don't really like this. It's still curving upwards, but it's going to go down, okay, but curving upwards. In general, as b increases, the curvature upwards increases, so you'll notice that the steepest curve has the highest b value, and the most shallow curve has the lowest b value. As b increases, the curvature increases. All right, so should be familiar with those graphical things. Let's do one example here, and then we'll be good. So here we go. A capacitor is the part of an electrical circuit that stores electric charge. The quantity of charge stored decreases exponentially with time. So we're talking about quantity of charge, and we're talking about time, and we know that that quantity decreases exponentially. Stereo amplifiers provide a familiar example. When an amplifier is turned off, the display lights fade slowly because it takes time for the capacitors to discharge. You've probably seen that in several different pieces of electronic equipment. Thus, it can be unsafe to open up a stereo or computer immediately after it's turned off because it's still got charged in it. You don't want to get shocked. All right, if t, right, so here's important, variable definition. If t is the number of seconds after the circuit is switched off. So t equals 0 is the moment the machine is being turned off, right? If t is 1, that would be 1 second after it had been turned off. Suppose that the quantity of stored charge in microcoulombs is given by this. So the quantity of stored charge is our Q. Right, and we have the equation that Q of t equals 200 times 0.9 to the t. T is greater than 0 is our domain. Right, it's what t could be. So in A, we're supposed to describe how the stored charge changes over time. If our b value is 0.9, then we know r for a decay will equal 1 minus that b value, which gives us 0.1. This tells us that the amount of stored charge, right, decreases by changing this to a percent, 10% per second. In B, we're asked for the quantity of charge that remains at different times. Right, so coming up. So coming down to here, right, my quantity of charge after 10 seconds would be Q of 10, and then I have after 20 seconds Q of 20, Q of 30. After 1 minute, time is in seconds, so we have to change that. We would be looking at Q of 60 seconds, 2 minutes for 120 seconds, and then 3 minutes for 180 seconds. If we simply simply substitute those values of time, right, in the exponent of our equation. We can evaluate that by calculator. We get these values. So after 10 seconds, that charge has decreased from 200, that's our initial charge, to 69.736 microcoulombs. After 20 seconds, it's decayed to 24.315. After 30 seconds, 8.4782. After a minute, a full 60 seconds, that charge is down to 0.3594. After 2 minutes, down to 0.00065. And then after 3 minutes, 0.00000112. So you can see those values for the quantity decreasing. Okay, for C, we're supposed to graph that charge over the first minute. So we would have a horizontal axis for T, and I've got that going from 0 to 60. And then Q of T is going to be in our microcoulombs. And our values went as high as, say, 70. So I think I'll take this. Well, it starts at 200. So if I make that 200, then this would be 50, 100, and 150. So if I'm going to graph this at time 0, the amount of charge is 200. Right? After 10 seconds, that is down to almost 70, so somewhere in there. After 20 seconds, down to about 25. After 30 seconds, down to less than 10. And then at 60 seconds, down to so close, right, to 0. So we're coming in, right? So for the first minute, I guess I don't need this, right? We're only going to there. All right, so our graph definitely, right, has that downward, right, decay of an exponential function. For D, we're supposed to find, all right, we're supposed to find the number of seconds. So we're supposed to find T for the charge to drop to 100 microcoulombs. So if we replace our Q with 100, we're trying to solve for T. Right? We know that at this stage of the game, we're going to do that graphically. So I get from here to here by dividing both sides by 200, right? Divided by 200. That gives me 0.5 equals 0.9 to the T. So we're going to go to our calculator, and for Y1, we're going to enter 0.5. For Y2, we're going to enter the exponential function 0.9 to the X. Right? So we graph those. We're looking for the intersection point. Right? So where is this intersection point? Right? Use that intersect feature on your calculator, and we get 6.579 seconds. Okay? So that's just a little bit more on exponential functions, focused on limits and horizontal asymptotes, otherwise pretty much using what we've done before. Oh, there's one other question I didn't answer. Let me go back to that. So in C, we were to graph the charge, and we were supposed to answer the question, what does the horizontal asymptote of the graph tell you about the charge? Well, this horizontal asymptote, as we would expect for an exponential function, is at y equals 0. 0 is a constant, so where we have a horizontal asymptote, we have a limit, and we know that the limit of our charge as t goes to infinity will equal the location of that horizontal asymptote, right? So that tells us that the charge approaches 0. And we could see, right, that after 3 minutes, although there was charge left, it was pretty close to 0. There wasn't a lot of it. All right, so have fun using that. I know you'll do a great job.